So, is everything clear up to now? More or less? So last time we have seen that at low temperature, the difference between quantum gases and classical gases become very, very important. In particular, in the case of Bose statistics, we have seen bosons. We have seen that there is this phenomenon of Bose-Einstein condensation. Now, it appears that this phenomenon takes place at very, very low temperatures. Temperatures of the order of a few degrees Kelvin. And indeed, at those temperatures, even very non-interacting systems, as a gas of helium, displays important interacting properties, so that the description which is given by an ideal Bose gas is a very approximate one. Even so, for example, helium-4, which is a boson, because there's 4 nuclei, and undergoes a phase transition at very low temperature, around 3 Kelvin, and this transition has some features of a Bose-Einstein phase transition, because people have measured the specific heat as a function of temperature, and this displays a cusp-like behavior like this, which is similar to the one of Bose, which we have discussed last time for Bose systems. And indeed, it was suggested that helium-4 may be described by, that this was a Bose-Einstein condensation transition. Indeed, the situation is more complicated than this, and indeed, there are Bose-Einstein transition has only been experimentally verified very recently, and there's been a Nobel Prize given to it, but not in this type of systems. Okay. Instead, if we discuss, if we go to Fermi statistics, instead the behavior of Fermi gases at low temperature is very, very relevant, as we will see, not only at very low temperatures. Okay. So what I want to do today is to discuss the behavior of, focus on the behavior of ideal Fermi systems, in particular ideal Fermi gases. Okay, so again, as we have seen, the thermodynamic properties of Fermi gas can be derived by the grand canonical partition function, which is given by a sum over all the states of the log of 1 plus z e to the minus beta times the energy of the state S. Okay, so these are sum over single particle. These are sum over the single particle states, and And this is the grand canonical partition function, so it's a function of the fugacity. So in order to get a description in terms of the number of particles, we have to supplement this equation with the equation for the number of particles, which is given by summing over all the state times the average number or the occupation number in state S, which is given by this formula. Okay, so all the changes is this +1 instead of the -1 for the previous case. Okay, so again, it is convenient. So we are going to discuss ideal gases. So the Hamiltonian of single particles. So the energy states will be h squared k squared will be of this form. Okay. And where, again, we are going to discuss particles in a finite volume V, so that this momentum will be quantized. And in this, so we can turn this sum over the states into integrals over the energies, okay, in the usual manner. So the integral over the state will be an integral over the energies with a density of state, okay? And the density of state is derived in the usual manner and is 2 pi okay, where with respect to the previous case I have introduced the factor G, and this is accounting for the degeneracy of each quantum state for the internal degrees of freedom of the particles. So while this factor can be taken equal to 1 for bosons, and of course we can also discuss bosons with some internal degrees of freedom. For fermions, this is not possible, and the reason is that there is a connection between, which I'm not going to enter into, between the statistics that the particles obey and the spin that particles have. So bosons have integer spin, whereas fermions have half integer spins. Okay, so it means that at least for each energy eigenstate, there are 2 eigenstates of the spin for particles with spin 1/2. Okay, so we will take this factor G in our calculation. Now the other thing is that the number of particles in each energy level for a Fermi system can be at most 1, okay? Or it can be, in this case, at most G, okay? So when we pass from the sum over the states to an integral over the energies, even though the energy density vanishes at epsilon equal to 0, there is no need to consider explicitly the state with 0 energy, okay? Because that will at most be occupied by G particles, and so they will contribute a negligible amount in the thermodynamic limit, okay? So, okay, given this, we can write the equation for these 2 equations using the density of state. And and again, we can write these two equations in the form of functions, which are equivalent to the ones which we have discussed last time. But for a factor plus here, okay. So this is GP3 integral from 0 to infinity. Where again, in order to go from here to here, you need to do an integration by parts. But the calculation is exactly the same as we did last time. Okay? So there is an integral of the density of state, so it will be proportional epsilon to 1/2 times the log of this. And you do the integral by parts, and you get this equation here. I'm not sure about yes, no, there is a, so in general you write this as, so let me write it as in the book. So this is function f5 over 2 of z. This is f3 over 2 of z. There was a numerical factor missing where these functions f, so the function f nu of z is 1 over the gamma of nu times the integral from 0 to infinity dx x to the nu minus 1 . Okay, so now in order to understand the properties of now in order to understand the properties of the Fermi gas, we have to understand the behavior of these functions here. Okay, so all we have to do is to discuss the behavior of these functions. So, for example, if you write the equation of state will be the equation of state will be given by essentially the ratio between two of these functions. And so if you can compute z as a function of, if you can invert this equation and find z as a function of number of particle volume and temperature, then you can compute the equation of state. So now, again, at high temperatures, so if you look at this equation here, it has the form, again, it has the form n lambda 3 divided by g is equal to f to the 3/2 z. So if you are at high temperature or low density, then this will be small. Okay? this will be small, and this will correspond to the regime of Z where this function is small. Okay. Now you can see that all these functions are essentially proportional to Z. So all these functions are essentially proportional to Z in the sense that f nu of Z divided by Z goes to 1 as Z goes to infinity. Okay? Right, because and indeed what you can do is so the regime of small high temperatures and low density will again correspond to the regime of small Z. Okay, when Z is very small. So what we have to do in order to study this regime is to write an equation. An expansion for this function for small z, and the way to do this is to write this as take multiply z above and below, to write this as dx x to the nu minus 1 e to the minus x 1 plus z e to the minus x. So what I've done here is I have multiplied above and below by z e to the minus x. Okay? And now what you can do is to expand this term 1 over 1 plus z e to the minus x in Taylor expansion in z. So this will give you z over gamma of nu sum n going to 0 to infinity of the integral from 0 to infinity dx x to the nu minus 1. And then you have an z to the n, and then e to the minus n plus 1 times x. Sorry, this is, let me write it here. E to the minus n plus 1 times x. And now this integral as in the, yes, there is also minus 1 to the n. Okay, because there is a plus here. Okay? And then the integrals now can be done, and the result is that the integral is going to give me a gamma of nu divided by n plus 1 to the power nu. So if you take this integral and make a change of variables where y is n plus 1 times x, then the integral in y will be proportional to 1 over n plus 1 to the power nu. And then what remains is an integral in y, which is the gamma function. And this cancels with this. So this is just z times the sum n from 0 to infinity minus 1 to the n. And there is a z n plus 1 to the nu. Okay, so with this result we can discuss all the high temperature behavior. Okay, so in particular, so let me write this. So let me just write the first two terms in this expansion. So the first term is z, and then I have 1 minus z over 2 to the nu plus z squared over 3 to the nu plus. Okay? Okay, so for example, if we want to compute the equation of state, so the first thing is we want to invert the relation between Z and N. So we have that N, the density, this is the this is equal to F3 half. Okay, from here. So it will be equal to Z 1 minus Z over 2 square root 2 plus higher order terms. And now, if you want to compute, so this will be your small parameter. You want to compute Z as a function of as a power series in this small parameter and compute the leading order term. Okay, so what you can do is to set from this, you will set to leading order. Z will be equal to this, and then you will have 1 plus a constant times n lambda 3 to the gv. Okay, so the way in which you find this equation, this constant here, is by putting this expression in this formula here. So let's do it for just as an exercise. So so this will be n lambda 3 to the gv times 1 plus a n lambda 3 to the gv. And then I have 1, and here I only need to take, since I'm going to only care about terms which are proportional almost to the square of this small term, I only need to take into account the leading term of Z. Okay? Because the other will only contribute to higher order terms. So here I have just 1 over 2 square root 2 and lambda 3 g plus higher order terms. So you see, if you take this equation, then this and this cancel, and you have an equation where on the left you have 1, which is equal to 1, and then there is plus a minus 1 over 2 square root 2 n lambda 3 over gv plus higher order terms. Okay, so if this equation has to be satisfied, you see that a must be equal to 1 over square root 2. Okay, so we have found that we can use this equation to invert. We have found Z as a function of N at high temperature or low densities, and with this we can use. We can compute, for example, the equation of state at high temperatures. Okay, so the equation of state at high temperatures is well. Here I can use both above and below the expansion, and this will be 1 minus 1 over 4 square root 2 times Z plus higher order terms, divided by 1 minus 1 over 2 square root 2 times Z, etc. And so this is to leading order is equal to 1 minus 1 over 4 square root 2 times z times 1 plus, I'm taking just the first order expansion of this, 1 over okay. And again, if you take only the first order term of this is 1 minus this plus this is 1 plus 1 over 4 square root 2 z. And here, essentially, you can replace z by the leading order term. So this will be essentially, so the final result is that at high temperatures, the equation of state will look like this: 1 plus 1 over 4 square root 2 n under 3 g. So you see, in contrast to the, if you remember, in the Bose gas, so the first, this is the first the coefficient, the first coefficient of the virial expansion. So this coefficient was negative. Okay, so negative coefficient is what you find is when you have a sort of positive, attractive interaction between particles, because essentially the pressure comes from particles hitting the wall of the system. And so if the particles interact with other particles, their momentum will be interact with other particles which are inside the volume, their momentum will be reduced. So you expect a reduced pressure. In this case, instead, the first virial coefficient is positive, which is as if particles were repelling, at a repulsive interaction, and just for the opposite argument. Okay. So, in spite of the fact that particles here are not interacting, there is a sort of effective interaction effect which comes from the statistics. So, the fact that this is positive is a manifestation of exclusion principle, Pauli exclusion principle. Okay. And likewise, if you you can also consider other thermodynamic quantities. Well, again, if you compute the energy of the gas, in the end, you will have will be given by a sum over S of epsilon S divided by the occupation number. And in the end, what you have is essentially that this, when you go to when you change the sum over the states in integral over energy, leads to the same integral as the one you have here. The only thing is that there is a factor 2/3 missing. So the energy of the gas is 3/2 of PV over KT. So there is a factor 3/2 and a factor KT. So so that if you do this calculation, you recover again the relation that U is equal to 3/2 PV. Okay. Okay, so from this you can write that the energy is 3/2 of KT. Using this is 3/2 of N KT times this ratio of these two functions, f of 5/2 z f 3/2 z. So it is equal to 3/2 N KT for high temperature and low density. It is equal to 3/2 N KT times 1 plus 1/4 square root 2 N lambda 3 times GB. Okay. Now we can compute the specific heat of the Fermi gas at high temperatures. So the first term is just the derivative of this term here, so it's 3/2 NK. Okay, so this is just the classical ideal gas. The second term comes from the integral, the derivative of this with respect to the temperature. So of course, the specific, once I have specified the energy as a function of number of particles, temperature, and volume, then I can just compute the specific heat as a derivative over temperature, right? Okay. Now, so the first term is this one. So the other term I can argue very simply what this other term will be, because so this second term will be proportional to T times T to the minus 3/2. So this other term is proportional to 1 / square root T. So when I take a derivative with respect to T, what I get when I take the derivative of this term here, what I get is minus 1/2 T to the minus 3/2, which is minus 1/2 the same term, 1 / square root T, divided by T. Okay? So the coefficient which I get here is just minus 1/8 square root 2 times the same object which I have there. Okay? So you see the specific heat is smaller than what you get as a correction which is negative. So it's slightly smaller than what what you get in a classical ideal gas. Now, okay, so so this is the behavior of a Fermi gas at high temperatures. So even at high temperatures, there are small corrections. But really, what is I mean, the behavior is of Fermi gases becomes very, very different from the one of classical gases at very low temperature, at low temperatures. Okay. So when the temperature is small, again, these equations are correct, but in that case, Z will not be small; will be actually very large, and so this expansion here is of very little use. Okay, because typically, you know, this expansion is an expansion where which works when Z is less than 1. Okay. Okay, so how do we understand the behavior of Fermi gases at very low temperatures? Well, at so okay. So the key idea is first to consider the case where the temperature is equal to 0. Okay. So when the temperature is equal to 0, if you look at the mean occupation number of an energy level with energy E, this is given by e to the beta epsilon minus mu plus 1, where again beta is 1 over kT. So when the temperature goes to 0, you see, if epsilon is larger than mu, then when when temperature goes to 0, beta diverges. So this e to the beta becomes beta times a positive thing becomes very, very large, diverges. So you have 1 over infinite, and it's equal to 0. Okay. So this is equal to 0 if the energy is larger than mu. And if the energy is less than mu, then this is negative. So when beta goes to infinity, e to the minus beta times something will be equal to 0. So you just have 1. Okay? Less than mu. Okay, so you see the occupation number becomes a step function. Okay? So this occupation number, if you is a function of the energy of the level, it's a simple step function at mu. So it means that all the states with the energy less than mu are occupied. All the states with energy larger than mu are empty. Okay, and all the states with energy less than mu are occupied by just one particle. Now then, yeah.
The energy is equal to the case.
Well, the case where if the energy is exactly equal to mu, then this is 1/2. strictly speaking. Okay, so but of course this will not contribute much to the thermodynamic. This will not contribute to thermodynamic property because it's just one state. Okay. Okay, so this function is well, it's generally called the theta function. Okay, so probably you have already encountered this. So you write this as theta of mu minus epsilon. Okay. Now, then, in order to compute the physical property of my system at temperature equal to 0, what I only need to do is to compute what is the function of mu. What is mu as a function of n volume and yes, as a function of the temperature, of the density. And to do this, essentially I have to ensure that the number of particles which are in all the states which are less than epsilon, which are less than mu, is exactly equal to n. I have to count all the states with energy less than mu and impose that this is equal to n. Okay? So n will be equal to 2 pi GV over, this is my usual density of states, H3 times 2m 3/2 times the integral from 0 to mu, the epsilon to 1/2. That's it. Okay. And if you do this integral, this integral is just 2/3 epsilon to the 3/2, right? So you get 4 pi over 3 GV over h cube, and then there is 2m times epsilon, 2m times, this is mu, no? 2m times mu to the 3 over 2. Okay? So for so this is so from this you can get this an equation for is mu, which is equal to well, effectively is equal to if you so is equal to h squared over 2m times 3n over 4 pi g times v to the 2/3. Okay. Now this value, this is the value of the chemical potential at temperature equal to 0, and this has a particular name. So it's usually called the Fermi energy. So at temperature equal to 0, all the so in a Fermi system in general, all the states with energy less than the Fermi energy will be occupied. Okay. Likewise, you see from this you can also define a Fermi momentum, which is just the square root of 2m times epsilon f. And well, this would have an expression which you can derive easily from here. So now you can compute all your thermodynamic properties. So in particular, say you can compute the average energy. So the average energy will be just 2 pi GV over h cube half times this integral from 0 to epsilon f d epsilon to the 3 over 2, because it's epsilon to 1/2 times epsilon. So this is precisely the same integral as before, but instead of 3 over 2/3, you get a 2/5. Okay, so this is 5. So it's 3/5 of, and the other thing is that instead of mu to the 3/2, you get mu to the, or epsilon f to the 3/2, you get epsilon f to the 5/2. So the result is that the average energy, the internal energy of this gas will be 3/5 of n times epsilon f. What is remarkable about this system is that you can also compute the pressure. So in order to compute the pressure, well, what you can argue is that, again, the relation PV equal 2/3 of the energy still holds even at temperature T equal to 0. It's a very general relation. And so from this you get that the PV is equal to 2/5 n epsilon f. So you see the pressure of this gas is non-zero even at temperature equal to 0. So this is quite remarkable. So if you take a classical gas, the pressure goes to 0 linearly in temperature. If you take, as we have seen 2 days ago, if you take a Bose system, it goes to 0 even faster. If you remember, it goes to 0 as T to the cube. Okay. In this case, the pressure does not go to 0. And the reason is that essentially all these particles are packed into these energy levels. And if you change the volume, you will affect. You will change the energy level and then change the volume, the pressure. So, in particular, you see, since the Fermi energy is proportional to volume to the 2/3, to the minus 2/3. So this is you have. So this is proportional to volume to the minus 2/3. You have that at 0 temperature, the transformation, if you you have a relation between P and V which is similar to the one of ideal gas. So that PV to the 5/3 is constant. So if you keep the number of particles constant and you change the volume, you will have this relation for isothermal. I mean, this isothermal transformation at 0 temperature in this gas, and so this means that the Fermi gas, even at 0 temperature, is still alive. Okay, it's not. There is important thing going on. Yes.
But this expression still holds if we decrease the volume.
Yeah.
I mean, like if we try to localize the particles. So
Okay, so now you want to decrease the volume a bit too much. So.
the number of particles will not be conserved.
Sorry? Number of particles is concerned. Yes, you can think of a box with these fermions inside at 0 temperature, and you compress and you do and you compress the box, and you measure the pressure, and you will have a relation which is given by this.
I mean, if we try to localize the particles due to the uncertainty principle, I mean,
No.
the particles will not be like.
No. I mean, that is. Okay, so you see these particles will be localized in every particle will occupy one energy state, which is an eigenfunction of the momentum. Okay, so they will have the momentum which is completely specified, and the position which is completely unknown. So these are plane waves. Okay, so they are not localized particles. They are localized in K-space. Okay. So and okay, so how do we go about discussing the properties of this system at low temperatures now? Now, at low temperature, what will happen is that if you look at this function for temperature small enough, what will happen is that if beta epsilon minus mu is so if the epsilon minus mu is much larger than the temperature, than kT, then more or less you will have the same feature, okay? Because e to the beta epsilon minus mu will either be very small or very large, okay? So the real change which will happen to the occupation number is in a window of size kT around the chemical potential, okay? So in general, this function will look like something like this, and when again it will pass always at 1/2 here, and then it will have an exponential tail. So so this means that in particular, so the number of so the particles which are going to be important are those which have an energy close to the Fermi energy. Okay, so this is where the real dynamics will take place, or the real action will take place, because all these particles will be frozen in their by Pauli exclusion principle, and all these particles, all these energy states will be empty. Okay. Now, in order to discuss the regime where the temperature is very small, you need other approximations. Another approximation for these functions, f nu, which and these are discussed in the book. And in general, what you can see is that the functions f nu of z can be expanded in a power series of logarithm of z. Okay, so what I would like to give you simpler derivation of the specific heat in particular, or of the properties of this gas at low temperature. So, both if you consider the number of particles and the internal energy, so you have to compute integrals which are of this type. So an integral over the energies of a function of the energy divided by e to the, let me write it like this, epsilon minus mu divided by t plus 1, where t is kt, okay? Now, and I want to compute this for t very, very small, okay? Now, one idea is to take this, make a change of variable and call, let me call it x, the variable epsilon minus mu over t, so that this integral is an integral where x, when epsilon is equal to 0, will be minus mu over t. And the change of variable d epsilon is t times dx, so there is a factor t here, dx. There is a function f which is computed in mu plus t x, and there is e to the x plus 1. Okay? Now I want to split this integral into two parts. The part from minus mu over t to 0, and the part from 0 to infinity. So the second part is just, so the first part is, I can change x into minus x. So I can write it as integral from 0 to mu over t dx of f of mu minus tx divided e to the minus x plus 1. So this is just the part of this integral from minus mu over t to 0 where I've changed x into minus x. Okay? And then there is the part from 0 to infinity. This is still t, which is the same. Okay? Now, here I write, I can write that 1 over e to the minus x plus 1 is equal to 1 minus 1 over e to the x plus 1. Okay, so you multiply by e to the x above and below, and then you can see that this is true. Okay. Now, so the first term, you see the first term if I make this change here, so I get the first term, which is so in this first term, I can change back the integration from x to y, which is t times x. So, or epsilon, which is t times x. And in this first term, so this first term, where I take the 1, I have just the integral between 0 and mu in the epsilon of f of epsilon. Whereas the second integral is exactly of the same form as this, but it has f of mu minus t x, and it has a minus sign. Okay? So the expansion, so okay, so let me write it explicitly. Minus integral from 0 to mu over t dx f of mu minus tx into dx plus 1 plus the other integral from 0 to infinity dx f of mu plus tx. Okay, so we are, so this is exact up to now. We have not done any approximation. So you see this is interesting because this is precisely the integral of my function over all the energies up to mu, which is what, and there is a t here. So you see, if you set t equal to 0, then you will just get the integral over all the occupied states. But for low, very small t, what you can do is to essentially approximate this mu over t by infinity. Okay, so when you do this approximation, essentially, if your f is a function which is not is like a power, for example, and we are going to discuss only functions which are a power. So the part of the integral which you are going to neglect is will be exponentially small in mu over t. Okay, so if I approximate this integral from 0 to mu over t with an integral from 0 to infinity, the error which I'm going to make is only exponentially small in mu over t. Okay? So this means that I can approximate this integral by the integral from 0 to mu in d epsilon of f of epsilon plus t times the integral from 0 to infinity dx of f of mu plus tx minus f of mu minus tx divided by e to the x plus 1. Okay? And now the last thing is that if you now you can see, I mean, in this integral for small t, what matters is really the behavior of this function f around mu. Okay. So what I can do is to introduce here a series expansion, expand the function f around mu, and so I will get the well, the first term, which is just the same. Now, in the second term, I can just take the leading term. I can just take well, this difference. You see, in this difference, there is just f mu plus tx minus f of mu minus tx. If I do an expansion around mu, then the first term will cancel because it's f of mu minus f of mu. So the first term is twice the first derivative in mu times tx. So the third term will also cancel because the third term will be a second derivative of f. There will be 1/2 f double prime of mu times tx squared, but there will be the same term coming from here, okay, and they cancel, okay. So the next order term will be proportional to the third order derivative, okay. So there will be 1/3 factorial times 2, 1/3 f3 of mu times t cube, okay. So if you put this expression here, then what you find is that the next order term will be proportional to 2t squared times the integral times f prime of mu times an integral from 0 to infinity dx of x over e to the x plus 1. And the rest will be other corrections which are of order t to the fourth. Okay. Now the last step is that this integral can be computed exactly. There are several ways. One way is to compute it with residues. And the value of this integral is pi squared over 6. Okay? So the final result is that so the final result, let me get the number right. Yeah. The final result is that I can approximate. So this integral here is pi squared over 6. So that the leading order term is pi squared over 3 times t squared f prime of mu plus orders of t to the fourth. Okay? Now let us use this result to compute the specific heat of our gas. So the first thing we have to do is to compute. So one thing you can do is to use this formula to compute the the behavior of the chemical potential for small temperatures. Okay, and from this, so you have to use these. You have to do integrals of this type with f of epsilon, which is the square root of epsilon. Okay, and so the number of particles will be, well, it's 2 pi v over and then here you will have the epsilon f, the chemical potential with 3/2 plus sorry. So what you have to do is this integral here, no? So the integral which appears here is exactly of this form with square root epsilon. Okay. So what you can do is you will have precisely the same constant here. Let me call it C times this integral up to mu, which is 2/3 of mu to the 3/2 plus pi squared over 3 times t squared, and the first derivative is just 1/2 of 1 over of mu to the minus 1/2. Okay. So now you see that so to leading order this will be equal to epsilon f. So you see that the leading order behavior to the Fermi energy will be so if you solve now you can put here epsilon f. And the equation which you have is that well, you will have this constant times 2/3 mu to the 3/2 plus a correction which is exactly equal to this constant times pi squared over 3 over 6 of k. Well, this is kt over epsilon f to the squared. Okay. So you see, this is the equation which you have at temperature 0. So the correction which you have is of order t squared. So your chemical potential will be the Fermi energy plus times a correction which is of relative order kt over epsilon f squared. Okay. Likewise, you can compute also the equation for the energy. So you can use this formula to compute the energy. So in the energy, you will have a factor 3/2. So if So the first term of this integral, which comes from here, will just give you again the 2/5 of the chemical potential. And the other term will give you pi squared over 3 times the first derivative of this is 3/2 times epsilon f times kt squared times epsilon f to the 1/2. Okay. So the important point which I want to stress is now, if you look at now you can express the chemical potential as a function of n and volume and temperature using the equation which I wrote before. And and this gives you the energy as a function of n, temperature, and volume. Okay. So you see that the corrections which you will have to the energy are proportional to kT divided by epsilon f squared. This means that the specific heat at zero temperature, the specific heat at low temperature, which is du dt constant n and v, will have a contribution which comes from this. We'll have a contribution which only comes from the correction terms, and since the corrections are proportional to kT squared, the specific heat will be linear in temperature. Okay. And if you compute if you do the calculation and compute the coefficient, you get a factor. So let me. Let me take it from here. Yes, so it will be pi squared over 2 times kT over epsilon f. And the correction will be of order kT over epsilon f cube. Okay? Because the correction to all these formula will be of order t to the 4th. Okay? So you see, this is quite important. So the specific heat of the Fermi gas at low temperature is linear in temperature. This, of course, is different from the classical result where the specific heat is independent of temperature, but this we knew. So this is particularly important for when you consider the solids. Okay, so in solid you can think, in particular in metals, you can think that solids are composed of atoms in a regular lattice, and then there are some electrons which are in the conductance band, which can be treated as a gas, as a gas of electrons, and in particular, if you compute, say, if you take a particular a particular metal like sodium, and you compute what is the Fermi energy corresponding to the typical density of sodium, you take essentially in order to, so the Fermi energy depends on the density, right? So the number of particles the number of electrons per volume. So in order to compute this number, you have to look at the elementary cell, how many atoms are there in the elementary cell, how many electrons are in the conductance band for each atom. Okay? So, and if you do this calculation, what you find is that this Fermi energy is of order of some electron volts, and which corresponds to temperatures which are of order 10 to the 4 or 10 to the 5. Okay? So it means that if you take a metal, even at room temperature, which is 10 to the 3 Kelvin, room temperatures for the metal are very low temperatures. Okay, so this so the behavior of a Fermi system at low temperature is essentially relevant for describing the behavior of electrons in a metal. Okay, and indeed, when you look at the specific heat of metals, so when you look at the specific heat of a solid, as I told you last time, so you have to consider the different degrees of freedom which can contribute to the specific heat, which can exchange energy. Okay, so 1 degrees of freedom are the vibrations. Okay, we saw well, the vibration can be described as very approximately as a gas of harmonic oscillators, and we saw last time that the specific heat which describes the specific heat of a gas of harmonic oscillator or a gas of excitation, bosonic excitations, is proportional to temperature to the cube. Okay, whereas the electronic degrees of freedom will contribute a specific heat which is proportional to temperature to the temperature. Okay. So there is so if you compare the two contributions, there will be a temperature below which the contribution from the phonons, say the vibration of the lattice, will be negligible with respect to the contribution to the specific heat of electronic degrees of freedom. Okay, and so, of course, I mean, this is just, say, first order picture, then one can compute more detailed properties, but the important thing is that Fermi systems, I mean, the behavior of ideal Fermi systems is much more relevant. Also, it has experimental consequences. So this number, this coefficient here can actually be measured. Okay, there are questions? So I think more or less, well, notice the last thing is you can always think of so in order to compute the specific heat, you always have to think about how many degrees of freedom contribute to exchanges in energy. And so the fact that the specific heat is linear here comes from the fact that the number of degrees of freedom which are which can exchange energy are only proportional to the temperature, because are only those which are in a range of the chemical potential of order kT. Okay, so all these all these fermions below a certain part cannot really exchange energy, and of course here there are no all these energy levels are empty. So the effect, the specificity is linear is related to this fact. And okay, so this is this I think concludes this course.